Math graphs are a powerful tool for visualizing the relationship between functions. They simplify the process of understanding connections between different equations. Thus, being able to identify most common graphs and their unique properties quickly is important. In this video, we will dive into some of the most common graphs used in math and engineering. For each graph, we will explore its equation, unique properties, and real-world applications. The first graph we will look at is the line graph. Line graphs are among the most frequently used graphs in physics and engineering. In general, a line graph is represented by the equation y equals m times x plus b, where m denotes the slope of the line and it controls its direction. A larger m indicates a steeper line. The constant b represents the y-intercept, or the point where the line crosses the y-axis, located at 0, b. Line graphs are commonly used for illustrating relationships between two variables. For instance, the velocity-time relationship can be expressed as v equals at plus v naught, where v is the final velocity, v naught is the initial speed, a is the acceleration, and t is the time. Absolute value graphs are widely known for their V-shape. The general equation for an absolute value graph is shown on the screen, with a vertex at the origin 0, 0. In a more general form, the vertex shifts to hk, and the parameter a controls the steepness or compression of the graph. For example, a larger value of a makes the graph narrower, while a smaller value makes it wider. Absolute value graphs are used to represent relationships involving magnitudes regardless of direction, making them ideal for scenarios like distance or error analysis. Errors can occur in both positive and negative directions, but the magnitude is what's important in most cases. Parabolic graphs are known for their distinctive U-shape and are commonly used to represent quadratic relationships. These graphs are described by the equation shown on the screen, where the parameter a determines whether the parabola opens upward or downward. The vertex located at a, k represents the maximum or minimum point of the parabola and can be calculated using the formula h equals b over 2a. Then k can be determined by plugging the value of h into the quadratic relationship. Circle graphs are fundamental representation of geometric relationships and are defined by the equation shown on the screen, where h, k is the center of the circle, and r is the radius. Circles are unique because they exhibit perfect symmetry about their center and maintain a constant distance from any point on the graph to the center. These graphs are commonly used in modeling wavefronts, designing gears, wheels, or circular components. Ellipse graphs are an extension of circles and represent stretched or compressed shapes with two focal points. The standard equation for an ellipse is shown on the screen, where h, k is the center. A represents the semi-major axis, or the longest radius, and b represents the semi-minor axis, or the shortest radius. Ellipses are symmetric about both axes and have unique properties such as constant sum of distances from any point on the ellipse to the two foci. The foci can be calculated using the following formulas. No matter what point we look at on the ellipse, the sum of the distances from that point to the foci will be constant. These properties make ellipses essential in modeling planetary orbits, which are elliptical with the sun at one focus. The hyperbola graphs are known for their two distinct minor image curves that extend infinitely in opposite directions. The standard equation of a hyperbola is shown on the screen, where h, k is the center, and a and b determines the distances to the vertices and asymptotes. Hyperbolas have two foci, and the difference in distances from any point on the graph to these foci is constant. These graphs are widely used in designing structures like cooling towers. The exponential graphs are characterized by their rapid growth or decay and are defined by the equation shown on the screen, where a is the initial value and b can represent growth if it's larger than 1, or if it's between 0 and 1 will represent decay. These graphs pass through the point 0a and approach the x as an asymptote for decreasing values of x. Exponential functions are widely used in applications such as modeling population growth or decay. Logarithmic graphs are the inverse of exponential graphs, with the general equation shown on the screen, where b is the base, a scales the graph, and c shifts the graph vertically. These graphs increase slowly and never reach the y-axis, which acts as a vertical asymptote. Cubic graphs have an S-shape and are defined by the following equation, where a determines the steepness of the curve, b and c affect the shape and orientation, and d shifts the graph vertically. These graphs have a point of inflection where the curvature changes direction, often at the origin in simplest form. Cubic functions appear in real-world scenarios like representing supply and demand curves with turning points. Sine graphs are periodic and can be represented with the equation shown on the screen. The amplitude A, frequency B, phase shift C, and vertical shift D define the wave characteristic. These graphs are foundational in applications like representing harmonic motion. Similarly, cosine graphs are periodic with the general form shown on the screen. Similar to sine graphs, the amplitude A, frequency B, phase shift C, and vertical shift D define the wave characteristic. These graphs are also used in representing harmonic motion, such as pendulum swings. Tangent graphs are periodic with vertical asymptotes and are defined using the equation shown on the screen. These graphs are undefined where cosine equals 0, resulting in vertical asymptotes. Tangent graphs are commonly used in analyzing wave interference and phase shifts. And this is it regarding the most common graphs in math and engineering. If you found this video helpful, don't forget to like, subscribe, and check out more content. Thank you for watching.